All right, so let's start. And then if some people join later, we can help them. So hi, everyone. Welcome to the Autonomous Origami Workshop. Salam, the workshop ما خوش اومدید. So we are really happy that you guys made it, and we are very excited about the time we're going to have together. So to officially kickstart our workshop, let me share my screen and go through some basic stuff. Oh, yeah, okay. So, hi everybody. This is me, Yasaman Tahoni, and Tiffany Cheng, who is here. So we are going to be your tutors for the following workshop, Autonomous Origami. So this workshop is provided to you by the Material Programming Research Group. We are a research group at the Institute for Computational Design and Construction at the University of Stuttgart. And the group is consists of me, Tiffany, Laura, and Dylan as our group leader. And Dylan will also be joining this workshop, not today, but in the following days. So this workshop is going to be 5 days. In the first day, which is today, we are going to give you more of an introductory lectures and introduction to material programming with fiber composites. And we will take a bit of a look at the origami and specifically Kirigami inspired mechanisms. Tomorrow, we are going to focus more on the origami and self-folding origami. And at the end of the day, we will give you the project briefs. And for the following 3 days, we will mostly be working on your ideas and we will develop them together for a presentation on the final day. So some notes. The first note about language. So as you probably saw in the workshop page, this workshop is going to be bilingual in Farsi and in English. So I'm the Farsi speaker here, and I will try to translate from time to time. For example, right now, ورکشاپ ما قراره که 2 زبانه باشه و من سعی می‌کنم که تا جایی که ممکنه قسمت‌های مختلف رو به فارسی ترجمه کنم. The overall idea that we have right now is that we will provide the lectures in English. We will have question and answer sessions in the breakout room, and this can be in Farsi or English, also the descripts. The Q&As, you can ask them in Farsi or in English, however you are comfortable with. And then lastly, the final presentation will also be in English. قسمت اصلی لکچرها ما اینا رو به انگلیسی خواهیم داشت. قسمت مربوط به سوال و جواب هر طور که راحت ترین، اگر راحت ترین به فارسی بپرسین میتونید به فارسی بپرسین، اگر که انگلیسی براتون راحته خب بقیه کلاس هم میتونه بهتر متوجه بشه. پس ترجمه به انگلیسیه. توی دسکریتا که روی پروژهتون صحبت میکنیم، چون که میتونیم بریم تو بریک اوت روم به هر زبانی که راحت ترین. و قسمت آخر هم که فاینال پرزنتیشن هستش اینم به انگلیسیه، به خاطر اینکه باید شیرش کنیم با دنیا. در مورد لکچرها چیزی که ما حالا خواهیم دید با توجه به اینکه شرکت کننده لول زبانشون چطوریه، اگر که مایل بودین و اگر که تقاضاش وجود داشته باشه ما میتونیم حدوداً 45 دقیقه تا 1 ساعت بعد از فرصت 3 ساعته ورکشاپ بمونیم و من اون لکچرها رو دوباره به فارسی بیان کنم. این بسته به نظر و ایده شما داره. And then the last point about interaction and participation, we try our best for this workshop to be very interactive, that you can participate. So we don't want to use these features like raise hand or stuff. So if you have a question, you can just unmute yourself and ask the question. You can also use the chat function to ask your questions, but I think simply having a flowing discussion and being able to unmute yourself and ask your question like we would do in a physical room, that would be a nicer setup. So I think this is the main thing for us. Okay, and then the outcome of the project, the outcome of the workshop will be project that you will do in groups of 2 to 3 people. And we will go through that more tomorrow with the specifications of the project. outcome نهایی این ورکشاپ هم پروژه خواهد بود که به طور گروهی ترجیحاً انجامش میدیم، گروه‌های 2 تا 3 نفره، و توضیح بیشتر اینو فردا میریم سراغش. و این بود از یک introduction خیلی کوتاه. This was our short introduction. So I will stop sharing so that we can actually start talking to each other. So I think we can first start with Tiffany, and then I will go ahead and introduce myself a bit more in detail, and then we will go one by one to you guys so that we get to know you more and you get to know each other. So
Yassi, that was a great introduction. And so yes, salam everyone. I'm Tiffany. I am also a PhD candidate at the Institute for Computational Design and Construction. I work very closely with Yassi on 4D printing. And I've been working here at the ICD for now 4 years. And originally I'm from Taiwan. I got most of my architectural education from America. So yeah. Thanks.
So this is Yassi. Yeah, my full name is Yasaman Tahoni, but you can just call me Yassi. I am an Iranian. I did my bachelor and first master's at the University of Tehran in Iran. Then I went to MIT and did my other master's there. And now I am at ICD doing my PhD studies. So if you agree, now we can go through the list that I have here, and you can introduce yourselves. So based on my list, which is alphabetic, based on the first name, we can go with Ali.
Hi, everyone. I'm very happy to be here. My name is Ali Bahmani, and I'm an origami artist, basically doing origami, not based on the codes or the programs, but more on the intuitive side of the origami. And I mainly work with the paper, and I studied mathematics and then museum studies in the master's degree. And now I work as a UX designer in a company. And we're joining this workshop together with my friend Ali Reza, who is also yeah. I didn't know anything about Grasshopper, so I asked my friend to be here and also help me with the more technical side and the software side. So we're happy to be here.
Great. It's great to have you. Salam, Ali Reza wa Ali. Great. So the next in our list is Azin.
Hi, everyone. My name is Azin Behfahani. I am a master's student studying product innovation in Los Angeles at the University of Southern California, better known as USC, at the Ivy and Young Academy. It's a school all about art, technology, and business of innovation. Before that, I did my undergrad also at USC studying business. And currently I'm working on just a personal side project that involves the origami physical component. So that's how I learned about this workshop and decided to apply, and really excited to be here, learn about Rhino, and meet all of you through this week.
By the way, I'm also a Trojan. I didn't mention where I got my education, but I did my undergrad at USC in the School of Architecture. So yeah.
Very cool. Roski, fight on.
Thanks, Azin. Great. Next in our list is Fatime. Fatima, we can't hear you.
Hello, everyone. Can you hear me?
Yes.
Hello, can you hear me?
Yes, we can hear you now.
Okay. Yeah, my name is Fatima Hassi. I studied architecture, Master of Architecture in Tehran University, and now I'm in Canada and study another Master in Architecture and Innovation in Rice University. And I work in my master thesis in origami geometry and how we can apply its geometry into architectural form. And I'm happy to here to learn more.
Great. It's our pleasure to have you. Thanks for introducing yourself.
That's it.
The next is Marina.
Hello, everyone. I'm Marina. I'm Brazilian. I graduated here in architecture, and then I pursued a master's in Barcelona in Universidad Politécnica de Catalunya. And my bachelor's final project was in origami, and I'm very interested in the subject. And that's about it. I'm currently based in São Paulo, Brazil. That's it.
Thanks, Marina. It's great to have you here. Oh, something happened to my list. Ferishte.
Yeah, hello everyone. I'm also happy to be here. My name is Ferishte Khojaslameh, and I have a master's degree in digital design from the University of Tehran, and I'm a PhD student at the Lightweight Structures Unit at the University of Innsbruck, Austria, and I'm working on active bending structures. I'm very excited about learning programmable material and joining this workshop. Thanks.
Awesome. Thanks. We are very happy to have you all here. Sorry if I forget to say it from time to time. And Bran, hello.
Hello. Yeah, I'm currently a postdoc researcher at the Hasso-Plattner Institute in Berlin. So my background is computer graphics and film and computer induction. I did my PhD in IST Austria in Vienna. And my research is mainly focusing on digital fabrication and computational design for 3D printing, laser cutting, and also paper cutting. So currently, I'm doing research on developable surfaces, which is kind of the basic of origami. So I'm happy to have this course and also want to talk to you. Yeah.
Amazing. It's great to have you here, Ryan. Yeah, Hasso-Plattner Institute is really cool. Yeah, I'm a fan of all the projects coming out of that institute.
Okay, thank you.
Great. Rasul.
Hi, my name is Rasul Fatolai. I'm from Iran. Currently, I'm in Shiraz. Actually, I'm a student. Actually, I'm studying building technologies in Bahmani University, and I'm interested in computational designs. So because of that, I submit for this workshop.
Amazing, thank you. Yeah, Shiraz. Great. Who was next? Roshni.
Yeah. Hi, my name is Roshni. I'm an architect based out of Bangalore in India. I recently completed my Master of Architecture from the Architectural Association School of Architecture in London. And I'm currently teaching at a university here. So I took up this workshop because of my interest in origami and programmable materials.
Great. It's great to have you here.
Thank you.
Saba.
Hi, I'm Saba Salehi. I'm a master's student in architectural technology at University of Tehran, and I don't have any background or experience in this subject, but I'm very interested in it. And I was studied about this hygroscopic material, and I'm interested to learn about it.
Great to have you, Saba. I also did architectural technology at the University of Tehran. So
Yeah.
that's a nice program. Okay, and last but not least, Shirin.
Hi, I'm Shirin Hossainzadeh. I graduated in Master of Architectural Design from Istanbul Bilgi University. And the topic of this workshop is one of my favorite topic, and I'm so excited to be here.
Great, we are excited to have you. Okay, so is there any comments or questions about the things I said before? The language, the daily schedule. If you have any question, please unmute yourself and ask it now.
Yeah, I have a question.
Yeah.
I want to know if you record the sessions, because tomorrow I cannot attend the workshop because I have to teach. And I just wanted to know if there is any way that I can access the meeting and yeah.
So that's a tricky question for me. We are doing a live stream, and I think it will be saved on my YouTube account at least. And yes.
Okay, thank you.
I will figure it out how to make it permanent so that you can watch it later.
Yeah, and if possible, please provide the link to the chat.
Yes, okay. The link is actually on the website, but I will put the link in the chat as well. Yeah, I will do it after.
Thank you.
Yeah. Any other question? So actually, now that we talked about the chat, if you open the chat, you see that we put a link to a Google Drive. So this is where we put all the necessary files for you. So right now, if you go to this and you can download day 1, don't download day 2 yet because they're still missing some files there. But for today, you can download day 1 and both the Rhino and Grasshopper files, as well as some papers for your additional reading are there so that you can go through them if you want. Okay. Any more questions? So if not, I will hand the session to Tiffany and she can start with the first lecture of today.
Okay, so I will start sharing my screen. Just one moment. Okay, so does everyone see my screen? It's okay? Okay, great. So the first lecture that we're going to give today for this workshop is to explain our approach in what we call material programming, which is taking materials as a starting point. In particular, we are looking at hygroscopic cellulose-based materials. And I'll broadly introduce the various works that our team is working on this topic. And as Yassi said, if there are any questions, please just feel free to interrupt me. I am happy to kind of not make this like a sort of one-way lecture, but also just have a lot more interaction during our workshop. But of course, if you prefer to sort of like wait till the end, we'll have questions and answers at the end as well. So just to start, when we think about how we traditionally make things, whether it's in constructing a building or manufacturing a car, it usually involves very complex processes, either mechanical or robotic, for the formation of the material. So most commonly, the example that we see with this is with CNCs and other methods of subtractive machining. or even in this example where the geometry of the curved crease is actually playing a role in determining the overall or the resultant curvature of the sheet metal, it still requires the brute force of two very large industrial robots folding it into shape. So what we're actually interested in our group is rather than starting with the robot or the machine, which is then imposing the shape onto the material, usually with high energy, with motors, controllers, robots, we're interested in rather inverting this relationship to allow the material to take a more active role in its own formation. So in nature, we see a very fundamentally different strategy from how we are making things and how we engineer things. So this concept of self-shaping, I think, is best exemplified with biological materials. And for instance, take the spruce cone, which can be found all over the world, including Iran. It basically contains hundreds of these individual scales that open up to spread their seeds when the conditions are dry enough for the seeds to survive and for them to travel far and wide. And the pine cone does this technically as a dead organ or a dead tissue. So in other words, it's basically disconnected from the supply of the living tree, meaning it's doing this without any energy, any metabolic energy. And the reason for this is that their tissues are hygroscopic, as you see in the cross section here, meaning these tissues try to maintain its moisture content in equilibrium with its surrounding environment or the relative humidity that's in its environment. And this completely passive, robust, and also silent functionality, which is very different from robots or machines. This comes just from the material and how it's organized internally. So this, bio-inspired principle is something that the ICD has started researching for now over 10 years, and specifically looking at a composite of wood, veneer, and copolyester composite system in a bilayer configuration. So we've studied how we can harness wood materials to program them and respond to their environment, and even and at this scale, at this smaller scale, let's say, this wood bilayer can respond quite quickly to changes in its surrounding relative humidity. As you can see here, the moisture content is quite responsive to the surrounding relative humidity that is shown on the hygrometer. And in fact, as you can see here, it can be programmed quite robustly and precisely to basically open at high humidity and close at low humidity, as well as vice versa in the prototype adjacent. So this system, as you probably have seen before, has been tested and verified in several demonstrators already. So this is here shown in an indoor controlled environment. It was displayed actually in Paris in the Centre Pompidou, and also in outdoor ambient environments. And so the ICD has been working on showing that architectural elements can be very highly in tune with our fluctuating environment. And this is created just by using the natural capacity of wood. In other words, we're not really giving the wood any new features. This is just something that is inherent into the material. And also at increased depths and scales, this principle we've also more recently applied to the manufacturing of curved timber components for architecture. So not necessarily like a continuous self-shaping, but self-shaping as a manufacturing process, and is basically locked into shape once the shaping is complete. So this is a technique that was showcased in the Urbach Tower, which Dylan, our third workshop leader, will present on day 3. So I will just leave it at that for now. And so, so actually any piece of wood can perform these functions. And what's impressive is that the wood does so without with such swelling forces. And it's, again, this principle goes back to the built-in cellular arrangement of the wood, which is influenced by how the boards were sawn, how they were like harvested, and as a result of how it's sawn, then the grain is different, right, in the individual boards. And also there's natural variation existing even within each board. And these are things that we can't really control or customize so well. So as a result, there needs to be a high quality of control in the selection and processing of the materials for a desired fiber direction. And this gets more and more difficult when we want to create complex geometries, or if we want to create mechanisms beyond bending. So for example, here, this is a sort of many units of a board on one surface that's been cut up and rearranged sort of like a puzzle piece to create a curved crease folding geometry here. So that brings us to 3D printing, which is also a topic that Yassi and I are working a bit more focused on. And interestingly, with 3D printing, the process of the printing creates this fiber structure that in some ways is quite similar to wood grain. So instead of sourcing natural pieces of wood, then we can use 3D printing to actually structure the material and tailor its internal composition through the paths of material deposition. And so to 3D print or quote unquote 3D print wood, we use the fused filament fabrication, or otherwise known as FDM, fused deposition modeling 3D printing technique, to basically construct these bilayer units. And typically we are using a combination of two materials, which we select or engineer. And usually this is a pure thermoplastic and a cellulose filled filament, which acts respectively like a active and a restrictive layer, which we'll go into more depths when we go into the paper programming part. And by mixing these thermoplastics with various types of percentages or fillers, we can access a whole range of properties. So this is when we actually engineer the material, the filaments. We also pretty much print everything flat, which dramatically reduces the speed when compared to conventional 3D printing. So in one process, we can also create the responsive parts in different sort of densities and different curvatures, and even print the support structures that interface with the building components in one process. And so this can be used to create sort of these adaptive elements that can be mounted onto existing architectural infrastructure. And line by line, we can customize the internal structure of an object however we want. So in the initial work that we've done with 3D printing, we demonstrated the ability to replicate the capacities of wood in the same aperture design and achieve basically a similar type of self-shaping through 3D printing. But with 3D printing, we can actually further customize the mesostructure with more complexity in the print paths. And this then allows us to create parts with programmable properties, bending directions, timing, and sequence. And to do this, we also developed the complementary computational tools for programming these varieties of shape changes. It's interactive and lets us quickly visualize the shape change, and the result can be directly 3D printed. So we'll also introduce some of these digital techniques in several tutorials throughout the workshop. But just to give a broad overview of the various kind of mechanisms that we can produce. For instance, this one that expands substantially in size from a very small footprint. And these structures, for example, this Kirigami inspired structure, which Yassi will also explain a bit more in detail in the next part, can be quite easily fabricated. So now we can say that complexity is relatively cheap, even for shape change. And similar to the sort of hundreds of these scales on a pine cone that we see in nature, then we can print these all these parts and layers in one manufacturing process. So we're also, of course, doing a lot of explorations on cell shaping using origami-inspired geometries. Obviously, this is the focus of our workshop for Inclusive Futures. And we'll also go into more depth on how curve folding can amplify movement in order to maximize the effect of shading, for example, in building facade systems. So we'll learn about that in the next parts. And also how potentially using origami tessellations, these can be used to create all sorts of self-stiffening origami structures by increasing the depth of the surface. So, so I'm just giving sort of a broad overview at the moment, but lastly, just to say that we're also interested in biology and what we can learn from plants to create adaptive wearable devices or other engineered material systems which can perform these functions without any energy, sensors, motors, or controllers. Yeah, so before we go into more of these projects that I've shown just very briefly in more depth in the coming days, I think we can open, if there are any questions, before I pass it on to Yassi for the introduction to our first tutorial. If anyone has any questions, feel free to ask.
Can I ask a question?
Yeah, sure.
So some of the examples you showed were not only opening, but also getting back to its former shape. Were they like, are you using heat to open them up and also cool them down to get them back to the first shape, or how they were like reacting to the opening?
Yeah.
And
That's a great question. So we're working mostly on natural fiber composites, cellulose-based material systems. And for these types of materials, they're responding to the moisture stimuli. So actually there's no heat. Well, heat, of course, like temperature does link to, let's say, the moisture in the air, but what's actually driving the shape change is the moisture. And so, you know, in the environment, we know that when it's raining, there's a lot of moisture that's being held in the air. And because of this hygroscopic property in the material, you know, the material is trying to equalize with the like the moist air. So it's absorbing the moisture and it increases the moisture content of the material. Does that answer the question?
yeah, thank you.
Tiffany, if it's okay, I will just say it in Farsi as well
for
the others, because I think this might be a question for other people as well.
Yeah, it's a very important point.
Yeah. So سوال این بود که این ساختارهای تغییر شکل پذیر دقیقاً به چه چیزی پاسخگوان، چه چیزی باعث میشه که اینا تغییر شکل بدن؟ و جواب اینه که ما به طور کلی هر چیزی که توی این پرزنتیشن نشون دادیم اینا موادی هستن که توشون سلولوز داره و اینو از چوب بگیریم توی نمونه های اولیه که نشون دادن تا سازهای 3D پرینت شده. فیلامنتی که ما توش استفاده میکنیم توش براده چوب داره یا سلولوز داره. چوب هم که خب توش سلولوز داره. حالا یه ذره دیگه میگیم که کاغذ هم توش سلولوز داره. به هر حال هر چیزی که توش این فایبرهای سلولوز داشته باشه هایگروسکوپیکه. به این معنی که اگر که رطوبت بهش بخوره باد میکنه. و بعد همونطور که تیفانی توضیح داده، حالا بیشتر توضیح میدیم، این خاصیت باد کردن که در حد 2-3% حجمی هستش، یعنی خیلی ناچیزه. ولی وقتی ما میایم اینو به شکل یک استراکچر بایلیر یا دو لایه قرارش میدیم این بادکردگی تبدیل به خم شدگی میشه. ولی صرفاً تریگر یا چیزی که باعث این تغییر شکل میشه رطوبت، حالا یا آب پاشیدن باشه یا رطوبت هوا باشه اگه که از هوای خشک وارد هوای مرطوب بشه. Okay, I'm done.
Yeah, maybe I also would just quickly add that, and so I've explained a little bit about the theory of material programming using this cellulose based material. And I think what's important for this workshop is that, you know, a lot of the materials that we work with, these natural materials, they have this property that it absorbs the moisture. And we want to just, I guess, say that this is a way that we can program just by arranging the materials in different ways. We can program these behaviors, right? So it's not like, it's not necessarily, it's similar in concept to digital programming, but instead of using, you know, bytes, ones and zeros, we're actually using materials to like with these properties, right? And putting them together. So I think with the paper, it's one of the easiest or accessible, inclusive ways to program actually. And by, for example, selecting papers in different orientations, putting together, it's very similar with what we do in 3D printing, what we do in wood. So, so yeah, I mean, I think that's probably a key concept that I want to somehow express.
Yeah, I think I'm going to talk a little bit about that too in this next slide. And then better is that we are going to make them ourselves with some paper and plastic, and then that would become clear.
Does anyone else have any questions about what we showed so far? If not, we can also
yeah, I can go through these last few slides.
Okay.
And then you can take a short break and then the tutorials. Okay, so now I am going to talk to you about how the structures that we showed you, that Tiffany showed you, we can kind of replicate them with paper. And this is what we're going to do mainly in this workshop. So paper is composed of around 90 to 95% of cellulose content. And as you know from Tiffany's workshop, cellulose is what makes wood structures or our 3D printed structures hygroscopic and make them and enable them to absorb moisture from the environment and change their shape. So the same cellulose, we have it on the paper. So we can use normal paper to create similar hygroscopic structures, meaning structures that can change their shape, that can open and close, or that can bend in response to the moisture in the environment. Next. Okay, so this is the very basic mechanism and the basic principle for creating shape-changing structures with paper. There is a concept called, there's a mechanism called a bilayer mechanism. A bilayer consists of two layers that are bounded together, glued together. One of these layers have the capacity to expand or shrink volumetrically. This we call it active layer. The other layer does not change shape, does not expand or shrink. So when we have these two layers bounded together, and if we expose them to the stimuli, in the case of paper, to the moisture, the paper wants to expand and shrink, the plastic wants to keep its shape, and because this expansion is constrained by the plastic, the overall structure bends. So this is what you see in these images here. And this bending, so if you have volumetric expansion and shrinkage for like 30 3%, 4%, very little. This bending is actually really large. So here we kind of have a motion amplification mechanism. And this is the basic component of the shape-changing structure that we are going to explore in this workshop. Okay, next. So the same thing that we saw in the wood and in the 3D print, that there is a directionality that defines the bending direction. We have the exact same thing with the paper. So paper is composed of fibers inside of it, and these fibers are arranged in some direction. It depends on the manufacturing of the paper, where it comes from. We don't care about that part. But what we care about is that we need to understand that in one sheet of paper that we have, what is the directionality of this sheet of paper? And then based on that, we know that if we make a bilayer, if we cut strips on it and we make a bilayer, what orientation the strip is going to bend. Next slide. For example, here, you see on top, if the fibers are oriented longitudinally in a long strip of a bilayer, the bilayer bends normally. But then if the fiber direction of the paper is kind of oriented 95 degree, related to the boundaries of the bilayer that we are cutting out, our bilayer kind of twists. This is because it wants to bend on this 45-degree direction, on the direction that is shown on the left-hand side image. And as it is bending in that direction, the overall strip kind of just twists around each other. And if we want to make maybe like something a bit more complex, like what you see in the lower row, where we have different flaps and we want each of them to open in a specific direction, the upper one to the top, the lower one to the bottom. So we need to orient the fibers. And the way to orient the fibers is to actually cut it from a piece of paper or orient the part on our piece of paper with the direction that we're supposed to. So this is something that Tiffany is going to explain more in the hands-on tutorial, but this is just to let you, just to give you an introduction of this topic of directionality of the fiber anisotropy in the normal paper. And then the last concept that we should keep it in mind is the bending direction. So what we talked before about the fiber orientation, we call that kind of stuff bending orientation. Bending direction, we mean if a piece of bilayer is bending upwards or downwards. So if you look at it from the top, if it's concave or convex, and that is just like no trick here. It is if you have paper on top, plastic on the bottom, it will go convex. If you flip it, you have plastic on top, paper on the bottom, it will go concave. And this is like even like meaningless in one piece of bilayer. But if you look at this slide, you see that by switching the placement of paper and plastic, you can create kind of this like S-like structure. So like convex, concave, convex, concave. And this is how you will definitely need to use that in any kind of prototypes that you want to make. So these are some, just keep them in mind, and we will go hands-on in a few minutes and we will try them, and that will make everything more clear. Okay.
So I think, we can also have questions now, but I thought before we get into the hands-on tutorial, maybe we take a short break. I don't know how much time we would need, maybe 5 minutes to prepare all the things that we need. So just to summarize, we sent this list out before, and for this particular exercise, it's less about the computer, but more with the paper. And ideally, you have several types of paper. You have some type of tape, cutting supplies. I have both an X-Acto knife and a scissor here. Also useful would be like some rulers, a cutting mat, and a spray bottle with water, with tap water is fine. So before we go into that and take the short break to prepare all these materials, is there any question about what we've seen so far from Yassi's introduction or anything else? Okay, if not.
Oh, wait, sorry. If you have any question in Farsi, اگه کسی سوالی داره اگه میخواین فارسی بپرسین کاملا راحت باشین فارسی بپرسین. Okay, no questions. Okay, so just to make it clear, we will have 5 minutes break now. Then we will have some physical prototyping tutorial. After that, I think we can have like 10 more minutes of break, or we stay here, but we will ask you to install the software. We will have a short software tutorial on the bilayers. And then after that, we will have a lecture on Kirigami. And after that, we will have a lot more hands-on prototyping with Kirigami. Sounds good? I hope so. Okay.
Okay, see everyone back at, let's say, 55.
Exactly 6 minutes from now. Cool.
No.
اگه کسی سوالی داره الان هم میتونید ازم بپرسین. If you have a question, you can just go ahead and hear. Oh, we have somebody new. AM? Or not new? Sorry, maybe I got confused. Yeah, we have two Aussie. Okay, this is actually kind of our surprise that not everybody who signed up joined. I think we had 100 applicants and we accepted we accepted some people, and at the end, 16 people confirmed their participation. So we thought we would be a bit more, but I think the less group size means more time for people who are here. So I think you've noticed, but in the chat, I am also like translating some keywords. توی قسمت چت این بغل من چیزایی که تیفانی میگه یه مقدار به فارسی ترجمه میکنم. اگه میخواین روی نگاه کنید و اگه که سوالی هم راجع به ترجمه داشتین راجع به کلمه ها میتونید به جای اینکه خودتون آنمیوت کنین توی چت بنویسین و من در لحظه سعی میکنم که ترجمه کنم. اوکی.
ببخشید من یه سوالی بپرسم.
بله.
این پترنایی که دادین رو الان لازم داریم پرینت کنیم؟
پترنا نه، اون واسه بعد از کریگامیه و حالا اینم توضیح میده که لزومی هم نداره که پرینت کنیم. من خودم پرینتر ندارم. کاری که میکنم اینه که اینا رو میذارم رو مانیتور، بعد یه کاغذ میذارم رو مانیتور، اینطوری شروع میکنم باش میکشم.
نصب این فایل چیزو ولی امروز میخوایم توی گراساپر، چون ببخشید من وارد نیستم دارم میپرسم.
آره نصب این فایل ها رو میخوایم، ولی حالا اگه میخوایم اینو توی یه بریک دیگه خواهیم داشت یا حدودا یه رو. اگه مشکل با نصبشون دارین توی اون یه رو میتونیم با هم صحبت کنیم. اینو توی بریک بعدی.
الان چیزی که لازم داریم کاغذ و کاتر و در صفحه برش و اسپری آب و این
چسب‌نواری.
پهن باشه؟
نه باریکم. اوکی. Okay, so there was just a question about what we need at the moment, what we need at the moment is just the stuff that you see here. And then the software parts, we have put them on the folder that we shared with you, and we will need to install them. But for that, we will have a 15-minute break later that you can install them. And if you have any problems, we can talk and help you through that. So that will be in, I think, half an hour from now, 45 minutes from now.
Okay, let's see. Okay, so I think we're ready to start. Everyone probably has all their tools and what would be good. So I'll just explain what we will do right now. First thing I'm going to show is how to determine the paper direction of the paper that you're working with. And the second thing is to construct basic bilayers. And with different, let's say, paper types, then you can even get different types of curvature. So, and with this paper, it's actually very soft. The curvature is very tight. With this one, it's a little bit harder, like a little bit thicker. So with that, we can also create less curvature. And then this one is a very thick material, a cardstock paper, which creates a very large bending radius. And also it's a lot more stiff than, let's say, this thinner material. So these are kind of the properties that we have to program with. The second thing, or sorry, the third thing that I will then introduce is how we combine the different bending directions into one part. So here's a very simple structure where we have alternating bending directions using the same material property, the same material type. And then the fourth thing I will go over is how to program the bending magnitude. So for instance, we saw that there are two different types of papers, or actually rather three, but here I combined two of them, where one has a tighter bending radius and the other one has a more has a larger bending radius. So these are ways that you can combine these properties together. And another technique to do this is actually to vary the amount of tape that is behind. So with adding the tape, we're actually increasing the bending stiffness of the material. So here I have like one layer of tape here, 2 layers and 3 layers. And that's also another technique that we have to change the bending magnitude across one part. So the first thing that I will show, and it would be great if everyone sort of follows along, and that way if you have any questions or you encounter a problem, then we can address it right there. So the first thing, and also the last thing to say is I'm just using this regular tape. I'm just using one type. So in the future, you can also consider if you have different types of tape, if you have, let's say, duct tape, which is very thick, that can also be one way that you make the material stiffer or decrease the bending radius, etc. So there's really a lot that we can do with just this type of material system. I just use one tape for now. Okay, so the first thing, let's say that we have just any old piece of paper. This is just printing paper. And one way to tell the bending direction is to actually look in the light. I don't think, well, you can maybe sort of see a little bit of the bending direction here, but if your paper is, for instance, too thick, this only really works with thinner paper. So usually you can tell maybe with a thinner paper the direction, but if it's too thick, what I usually do is I make a test piece. So essentially the system is just putting tape on top of the paper, right? And then what you can do is then cut this off with an X-Acto knife or a scissor. And then you take this piece, cut it out. This is your test sample piece. And you should remember the orientation in which you cut. So what I'll do is I'll actually spray this. Okay, so then you can see very quickly, right? It's quite fast that the bending direction is this way. So what you can do now, I hope everyone can see, but if you're having trouble seeing, just please unmute yourself and say something so I can rearrange my camera. So what I also like to do is I just make like a mark on the paper. Okay, this is the grain direction. So then I always know, right? In that piece of paper. And usually paper, the way that it's manufactured, it's always sort of orthogonal this way or this way because of the way that it's produced. So I would say rarely is it going diagonal. I haven't seen that so often. So usually it's going to be either 0 degrees or 90 degrees, and you just have to check. So does everyone, is everyone following? Is it okay?
Yes, it's okay.
Okay, great. So we've seen
how Tiffany, can I say something here?
Yeah.
I was thinking that if you have like thinner tape, what you can also do is to have like to take one piece, if this is your paper, like put one piece like this, one piece like this. So like 2 strips in like arzi or amudi or fupi, like a horizontal or vertical, cut them, spray them, and see which one is bending nicely. And then that would be the direction of the paper. So this is what I did with this piece.
Yeah, so similar, like a test piece, right? To sort of quickly see.
Exactly. Just like cutting 2 or 3 pieces in like different directions in the paper to see which one is the best paper direction.
Yeah. Yeah, usually it's pretty simple. It's always orthogonal. And I've already checked these actually. So with these ones, the grain direction is actually this way. So these 2 pieces of paper, this one's a bit thicker, this one's a bit less, this one's a bit thinner, this one's a bit thicker. And let's make this one. So this is just a combination, right, of the 2 papers. And so with this, it's also quite simple. You can sort of manufacture them in one go. So if you want to start combining some pieces that way, then what you can also do is just simply put a tape on this way at once and create this bilayer. And I just use a ruler to flatten the tape onto the paper. Okay, so. And if you want to, let's say, combine like 3 different pieces, you would just add 1 more piece of paper here. That's a different property. For now, I just have 2 here. And then I'm just using scissors because it's faster, but if you're more precise, you can use an X-Acto knife. These are just really quick and dirty ways to get started. Okay, so now you have 2 pieces stuck together. And then I'm actually going to make this a bit shorter. Don't want it so long. Okay. So to make this piece right here, this is just a similar one. And I'm going to spray the water on one side. And then you can already see that it's starting, right? The white one is moving a bit faster than the pink. Okay. So,
Tiffany, should we take like 5 minutes so everybody can make a basic bilayer?
yeah, sorry, I might be going too fast.
Yeah, let's
Okay.
just wait for 5 or 10 minutes and everybody makes some, and then they can show it under the video to see, and we can check if everything looks good.
Yeah.
Or
that's
there's a
good idea.
Yeah.
Okay, so
Excuse me, can I ask a question?
Yeah.
So by bilayer, you mean a layer of tape and a layer of paper, right?
exactly. So
Yeah.
here is the tape. It's shiny, and then here it's matte. It's paper.
Yeah, and so we should spray all the surface of the paper.
Yeah.
Because if we just put water in parts of it, just that part bends.
Exactly. Yeah. So with direct water, you actually could spray one side first, but usually when we're talking about hygroscopic systems and just responding to humidity, then it almost uniformly becomes moist. Yeah. So we're using water because it's really fast to show.
Okay, thanks.
I mean, you can try putting your paper bilayers on top of some steam. I don't know if you have a water boiler or something. You would see that even with just the steam, it will bend, especially if you have thinner paper. But we spray water. But yeah, we spray water everywhere. And I mean, normally the side that there is the tape, the water don't go through, so it doesn't matter. But should make sure to water the side that is paper so that it can expand.
Oh, you're muted.
Yeah, I just made one with thick paper and thin paper, and I get a nice spiral curve. The first one I made was a failure because I made a mistake in my thin fiber direction, and you can see that this part is bending nicely, but this part is just not right. This one is better.
If you're ready to share what you made, just so we can check, feel free to turn on your camera and say something.
Hi, I would like to share what I did. I think one of the papers, the initial paper I used was the printing paper, so it curled entirely to test like the direction of it. And when I combined it with another paper that's slightly thicker, I hadn't checked the direction of it. So the first result I got was something like this, where it sort of, this one had a uniform direction, but the other one didn't. It has this weird bend. So then I thought I should just check the direction of it. But then when I test it again, it has like a weird warp. So I'm not sure if the direction is not linear. I'm not sure.
I think maybe the direction is 45 degrees.
Yeah, I think so, because look at this. So the other one curled entirely, and this one has like this weird.
Yes, this one is kind of twisting.
Yeah.
So if you maybe you can like place one piece like
yeah,
this.
Probably.
And see.
Yeah.
Could you explain how would we be able to see the grain in the light?
So with that one, actually, that looks a bit weird. Because that's a very thin material, right? And I can already see through the light that it looks kind of mixed. Like it looks like it's but that's usually not so common. So why don't you, so usually you'd be able to see like a clear direction in the material. And I think you can even see it a bit in this one. I don't know if you can see it through the camera, but there is like sort of a directionality going this way. But for the paper that the other paper that you showed, I don't know, from the light, it's hard to tell. So with those types of papers, I would just put the tape on and then spray it to see what the natural curvature is. Sometimes you can tell by looking, sometimes you can't.
Yeah, and also in these A4 papers, if we put the tape in 45 degrees, then we have something like the grain is directional, right?
Yeah. So again, it depends on the paper. So check what the natural. So the natural direction is like the coordinate system of your paper, let's say. And so the coordinate system might be this way or this way. Rarely, I think it's sort of in a weird 45-degree angle, but if it is, then that is your coordinate system. It'll just be kind of oriented like that. So the boundary of your object is going to be relative to this coordinate system.
Thank you.
Hi, so I just wanted to show you, I tried it and I cut it at 45 and I got like a curve, and I tried looking through the paper even though it's relatively thick, but I see just one diagonal line when I look through the light, so I'm not sure if that's the grain, but yeah, it's evidently 45 because it entirely curved.
Yeah.
So it's really interesting, thank you.
Cool. Yeah, so then apparently there are some 45-degree papers too. Because like, yeah, usually it's just about the manufacturing of this paper.
I want to also share what I did. First, I tried with just the grain direction and make something. I don't know if you can see it. Yeah, it's the same that everyone also did. And also I cut 45 degrees from the paper and found this twisting.
Oh, nice. That twisted very nicely. Yeah. Cool. Your paper is very hygroscopic. It's curving very much.
Yeah, it's a very thin paper, just a normal printing.
Oh, Ali, you also got a twist, huh? Nice. Okay, so whatever direction that you cut that piece, you should go 45 degree if you want a single, like if we want a clean bend.
So I originally put the tape in 45 degree.
Okay, so now we still don't know if your grain is vertical or horizontal. Yeah, I mean this is what I do. Like, I write and I put the tape and I cut the three, I spray them, and then I know if whichever bends nicely that would be.
Actually, I made this with a very thin paper, so you can see it's very small cylinder, and also another one with a normal paper, and it's starting recovering to the normal configuration, I think. Yeah, because it's drying, nice. I think.
Yeah, I think if you have a thinner paper, it also dries much faster.
Yeah, and for this one, at the very beginning, it's very smaller, smaller than this, and for now it's becoming larger again. And I have another question that could it happen that in some situations have this kind of bistable configuration for the paper?
Well, not in a single bilayer, but if you make it into a bistable mechanism, if you design it as, I don't know, like two bending things in the opposite direction, or depends on the mechanism design, then you can Does that answer your question or?
Yeah, because I saw some material that can bend in this direction into a stable configuration, and also can bend in this direction.
No, like one piece of paper can't do that because it has this like built-in fiber anisotropy. But if you make a mechanism out of two, and then maybe one of them is thicker, one of them is thinner, so then like if you make a cross and then one is like quicker, one is slower, then maybe like you can have some bistable effect. Not sure. I haven't tried it before.
Okay, I see.
Excuse me. We dry the paper. We make it wet with water, and when it is dry, it still has the form, or it can change.
Okay, so this is a good question. If you will make it with the wood, when it goes back to dry, it goes completely back to flat. But with the paper, it usually doesn't go completely back to flat when it gets dry, because paper also has other chemicals in it. And like sometimes it's just the watering it makes some changes in the structure. But if you want to create a structure that is flat when it's wet and that is bent when it is dry, you can do that. So I don't know, Tiffany, are you going to show that as well? Like wet paper? Okay.
Sorry, yeah. My laptop died, so I kind of was gone for a bit. So yeah, I'm going to show that also at the very end. But yeah, essentially what Yasi is saying, you can actually do the reverse engineering where you are spraying the paper while it's wet and then putting the tape on. And as it's drying, then it's going to actually shrink on the paper side.
Yeah, so you will need to start with the wet paper before you put the tape. If you have thicker paper, you put it in the water for 5 minutes or something. If you have thinner paper, just put it in a plate of water for 1 minute. And this makes sure that the paper now has absorbed water and it's expanded. After that, you take out the paper, you wipe it a little bit, and then you put the tape on it. So now your wet bilayer is flat. And then when it goes dry, it slightly starts to curve. And I think I had some samples that I made yesterday that in the dry, they are now like completely bent. Or I will make one now and show you in 5 minutes.
Do we need to soak the paper, or can we just go back to spraying the water?
You can spray, but if you're going to do this type of construction, make sure that you spray rather evenly. Otherwise, pre-programming like a difference in the, let's say the programming, if you spray more on one side and you spray less on one side, right? That makes sense?
Okay, yeah, of course. Thank you.
Yeah, I mean, soaking just ensures that it is even and it is fully saturated, but you can also just spray it.
So my webcam, unfortunately, I realized is causing my computer to, like the battery to deplete very fast. So maybe I can't show like the table anymore, but maybe just quickly to show that I also started combining some of these together. So these were just 2 pieces that I taped together here. And, you know, by spraying it, then you can see that it starts to open up very quickly. Here is also one that I sort of did opposite. And then if you sort of spray, I think this one is not so fast actually, but it starts to open a little bit. And then we have this one, which already started, that I showed earlier, already starting to go flat. So, I mean, I think it's pretty straightforward, but what I'll do now is I'll start making this one. So I think this one should start to, you can see that it's starting to curl. And so with this one, I think everyone sort of can go along at their own speed, and we'll stop in a moment. But for this one, I just marked on this piece of paper. I measured 2 centimeters apart on both sides. So I'll just go ahead and do that. Okay, so I've marked 2 centimeters on both sides, which is important because you need to put the bilayers on both sides, and you want to know which side you've put, which side you're putting the bilayers on. So you have to mark both sides. And I will place, I'll also do the same with my tape. So I'll just take my ruler. Like this. I actually tape my ruler to the tape, and then I cut every 2 centimeters. And for this one, let's actually try to do the opposite, as we said, where we soak the paper first, or we spray the paper first.
Yeah, I'm also doing that. I soak them, so you can also watch. So.
Okay, so after soaking them, I've already pre-cut my pieces of tape, and I'm just going to place them in alternating increments of where I marked. So I'm going to place a tape here, here, and here. So I've placed my tape in alternating parts, and then I'll just do the opposite side, placing the tape on the in-between points. Okay, so now I have the array of bilayers, and I'm going to just clean the sides because it's a bit messy with the tape everywhere. So I'll just take a scissor and just clean the sides. Okay, so it's done, but now we have to wait for it to dry. So I'm gonna put this in front of my fan and then we can check back in like 5 minutes. How's everyone doing?
I have a question.
Yes.
So the reason for first making the paper wet and then adding the tapes is to make it work as the wood does? Is it right?
So actually not so much. The reason is because the conditions in which we are manufacturing it flat is going to be like what the shape is going to be when it's dry. And then when it's wet, then it is going to curve. So if we actually reverse this programming by manufacturing the bilayers when they're wet, then then it's the flat configuration is going to be when it's high humidity or when it's wet, and when it's dry, it's actually going to curve. So we're actually flipping the programming where it's going to curve when dry rather than be flat when dry.
Yeah, okay, thank you. But the other thing is that these papers, when they got dry, they changed their form. So, but I think Yasaman told that in wood, it's not the same.
Yeah.
Because it keeps the form. So I want to know how can we use paper and simulate the thing that happens in wood?
Yeah, that's a really good question.
Sorry, let me clarify something. Sorry, I think I talked confusingly there. What I was saying is that with the wood, when it goes wet, it bends, and then when it dries, it goes completely to flat. But with the paper, it doesn't go completely to flat. Like maybe it's, for example, I have a sample here that I will show later. You see, they are almost flat, but a little bit, sometimes a little bit still curvature that this is remains. So the only thing is that wood goes like completely clean back to flat, but paper not necessarily. But the thing that Tiffany said, we actually do the exact same thing with wood. So let's think of the application when we want to put it on body or on facade. We want to decide if we want things to be open when they're wet, or if we want them to be open when they are dry. And based on that, we decide. We do the same thing. We put the wood in high moisture for a long time, and then laminate it, make the bilayer. This would be the case of like putting paper first in the water. This case would be flat when it's wet and bent when it's dry. If we want the reverse scenario, we make the bilayer when it's dry, and then so when you spray water, it bends.
Yeah, maybe I can just explain a little bit more about why with paper we see this variability. It's because wood is actually quite special in the fact that it's maintaining its stiffness quite well, even when it's rather moist. But so for instance, if you compared like a wet piece of wood versus a wet piece of paper, then the wood is still actually stiff, and a lot of materials will lose their stiffness when they're moist. So one of the ways that you can try to prevent the paper from warping too much once it's going back to dry, as Yassi said, one way is to actually program the reverse, because when it's dry, it's more stiff. Another way is to use just a thicker piece of the bilayer. So with a thicker piece, it's also much more slow, but it's overall more stable, right? It has more stiffness, it's more stable. So with these, let's say, really thin pieces of paper, if you force it into a certain position, then it sort of stays. So that's why you get a lot of these variabilities, because it's so stiff that it's kind of, will sometimes warp depending on how the water is evaporating through the surface. And if you take a thicker piece of cardboard, then it's a lot more stable. So that's one way you can try to prevent this unwanted behavior. I don't know if that makes a lot of sense. Hopefully I explained it a bit more. So if it's still not clear, just let me know.
So Tiffany, I was wondering, is it also possible to combine the fold lines with this technique? Because especially with the curve folds.
Yes, that's a really good question that actually we're going to go into more depth tomorrow. So tomorrow we'll focus a lot more. So today is more about the introduction to material programming. Tomorrow, Yassi is going to give the tutorial on the folding.
Actually, I have a question.
Mm-hmm.
What happens if we put the paper under some pressure? For example, hang something from one side and let it dry.
Yeah, so I think that actually goes sort of back to the questions about like why the paper warps, because the paper is not so strong compared to wood. The swelling force in wood, as we know, in ancient times, is strong enough to break rocks. But paper is not really, it doesn't have that mechanical property. So actually, if you just take a really thin piece of paper, like the printer paper, and then hang it, you're going to actually reprogram it to let's say, so let's say you programmed it where it's wet and dries curved. And if you actually hang it when it's drying, you're going to change the internal structure, where then the default configuration is going to be straight, like because you're hanging it, you're making it, or if you put a weight on top of it, you're basically reprogramming it. Does that make sense?
Yeah. And just one thing, how many times it can wet and dry? I mean, is it something's happen in between? I mean, do we have any joints or something in real prototype?
So what happens in between is any bias that you give it. So for example, the weight, you're reprogramming it, right? So the difference between this and wood, and actually you can still do this with wood, but wood is much stronger in resistance to this. So, I mean, sorry, is that answering? I don't know if I'm going in a different direction with this.
No, the last prototype that you showed us, that the pink one, that rolling.
The rolling, you mean, sorry, the rolling one?
You paste the tape up and down the paper.
Yeah.
And put some needle in between.
Yes. So now actually, the point that we go back, it's now. So now it's
it has lots of joints between the paper.
Yeah.
If we want to make it by the real prototype, I mean the wood, how many times we can dry it and let it wet?
Okay, with the wood, actually, there's not really so much of a limit. Like it will continue to actuate and it will continue to operate. But if you put the weight on it, then you're going to change the properties, right? So then if you try to actuate it again, then it'll perform differently. So as long as you don't introduce some type of bias into the system, if you don't strain it or load it, then it'll continue to actuate over and over again.
So you mean that the wood? Okay.
No, go ahead.
You mean that wood has no yield point, that the material can't go further? I mean, the point that material can't bend down or up? For example, in steel, I know that we should put some joints in between two surfaces because the steels can't bend as much as we want. It has some limitation in the number of how many times we can bend it or unbend it. Do we have that limitation in wood or not?
So we don't have that limitation in wood when we have this type of bilayer structure. Because if you like bend something with external force, yes, like you make it, I don't even know the expression, but
yeah.
But with the wood, with this hygroscopic property, because it's internal to the material, you're not putting any external force, it can go many cycles. And actually the best way to see it is in the pine cone. Oh, my pine cone here. So pine cone is kind of one of the best examples of a natural bilayer. And you can put this pine cone in the water, it will completely close. And then if you put it back, let it dry 1 or 2 days, it opens. And it does that many times. Actually, we recently read a paper that they have found fossils of pine cone with 10 billions of years or 7 billion years. And when they put that fossil in the water, it still moves. And when it dries, it goes back. So this is honestly an amazing property that these kind of actuators can just work hundreds and thousands of cycles without getting damaged, without using any energy. And you can also see that with the paper. Like, yes, maybe it doesn't go like completely flat or in the nicest way, but you see that this was the bilayer that I made 10 minutes ago. It curved, now it's back to flat. And then if I like put water again, it will bend again. And you can test that on the bilayers that you just made right now yourself, that you can do that many cycles.
Yeah. So we have no joint, the wooden prototype. That sounds great.
Yeah, exactly. These are mechanisms based on bending, compliant mechanisms based on bending.
Great. Thank you.
Yeah, and just to add to that, we actually have these. So this is the wood prototype. You can see that the wood grain is here. This is the veneer, this is the copolyester synthetic mesh that is on the other side. And we have this on the roof of ICD here, and it's been here, I think, at least 7 years, still operating. So, and I think, the reason, there could be some creep deformation because of maybe some type of loading, but because the stiffness of the wood is quite good, it's able to overcome any, wind load. So it's on the roof outside. And so I think a lot of that has to do with the stiffness of wood. And of course, like some of these really thin papers will have a lot of deformation, not completely repeatable motion. But so this is the one I showed earlier, the stiffer cardstock material. And now it's getting pretty flat, right? So it's a lot more stable in terms of the behavior because of the stiffness that this material has. And I'm going to spray it again and let's see if it makes that nice curve again. So we can already start to explore, with different types of papers. Some really thin ones are going to really warp because they just have no stiffness. They're going to be any bias like you give it, like if you press on it, if you fold it, things like that will deform it. But with a thicker one, you can mitigate these effects.
Thank you so much.
So can I, oh yeah, sorry. I will show something after you.
No. So I just sprayed this. Let's see, like because the thicker ones are also slower. The thin ones are really nice because it's so fast that you like understand. But then I think when you move towards like a nicer prototype, I'm doing this with like a scissor. I'm doing this with like just kind of roughly cutting things. But when you move on to the nicer prototypes, what you probably want to do is print patterns out of the computer, cut it with an X-Acto, do it nicely, and do it with thicker paper, which will give you a much more reliable motion. Okay, sorry, that's all I wanted to say.
I also have something very quick. So this is the sample I made with the reverse programming. I put the paper first in the water, then I put the tape on it. And as it dried out, it got bent. So I put it in front of the fan of my laptop. Some hot air comes out and make it dry faster. So now this will stay like that if it's just in the room. And if I spray water on it, now you see this like reverse motion, that this piece, when I spray water, it will go back to flat. It's like,
well, yeah, C sprays that. This one's the one that I made in reverse, which is now curving when dry. And I also spray this to get it flat again.
so yeah, this would be useful if you want to create pieces that are shaped when they are dry. And if you think of it conceptually, opening and closing in response to either drying or humidity is one topic. One topic that people talk about a lot in this like self-shaping and self-assembly is if you can deliver things when they are flat and then things self-shape themselves. So you can imagine that you can pack things with moisture, like a tight plastic bag or something wet, and then you put them in a tight postal box. The person takes it out, let it out to dry, and then the thing shapes itself after 1 or 2 days and stays in that shape as long as it is not sprayed. So yeah, this is still going back to flat. This is a thick piece of paper, so it takes some time.
And here, this is now pretty much flat as well.
Excuse me, yeah, the thing that you told about making the paper so that it keeps the form in the dry environment like the room is very interesting. And I just wanted to know the temperature of the water that we use for the first making it wet. Is it important, or does it have an effect on the?
Not really, no. It's the water saturation.
Yeah, it might make it a little bit faster when it's warm, just because usually when it's warmer, things can absorb quicker, but not so much in terms of programming.
Okay, so I think maybe we can take 10 minutes break or 12 minutes break. And in this time, it would be great if you guys can install the plugins that we have put on the Google Drive. So I can resend the link of the Google Drive here in the chat if you haven't got it. So our digital tutorial is not going to be too long. It's going to be longer tomorrow when we talk about origami. Today it's pretty simple, but if you can install them and follow, that's better. If not, you can also do it at a later time. And after that, we will have a small, like a 20-minute lecture on Kirigami. And then we will have some more prototyping, this time with a bit more exciting patterns based on Kirigami. Okay. We also, so on this Google Drive, you can also find this file called pattern. If you want, if you have a printer, you can print them in this break time, but it is also not necessary to print them. You can, yeah, I will tell you what to do, but if you don't want to print them, just, it's all fine. I don't have a printer and I still did it. Okay, so should we go take a break now and come back in 12 minutes? Okay. So I'm going to just copy the link here again and go to day 1. And then in day 1, you can go to example files. And there is a folder called resources. And those are the plugins that you need to install. So the software we need is Rhino. So I hope you have it installed now, or I hope you have some access to it. Then we would need Grasshopper. So on Rhino 6 or more, Grasshopper is pre-installed. If you have lower Rhino, please install that. And we also need a Kangaroo plugin. So that also comes with the Grasshopper and Rhino 6 or more, but if you don't have it, please install that too. So that is Kangaroo 2. And then the rest are some plugins in that resources folder, which are the older Kangaroo, and then Kangaroo Extra, which is something we've built ourselves, and Plankton and other plugins. So if you are completely unfamiliar with Rhino and these kind of stuff, you can text me here, or we can just like stay in this group and talk through it. I will go for 2 minutes, 3 minutes, and I will come back and then we can look at that, okay? Awesome. Okay, so now we see each other in 10 minutes. Sorry, I talked too much. Okay, I'm here if you have questions. اگه سوالی دارین راجع به نرم افزارینی من اینجا.
I had a question about installing the plugins. I followed the steps to, install it within Rhino, but I'm getting an error that like the plugin came from another computer and is blocked to protect this computer. And I follow the steps to allow it to still install, but I keep getting the same error message.
Oh. Ooh. Okay, let me see. So if you go to a special folder, components folder of Grasshopper, this is where you install it. And if you right click and go to properties in that component, do you see on the lower side in the general, do you see like lock or unlock button, something like that?
Can you share your screen?
Yeah. Yeah, I just noticed that I should have done that. Okay, share screen. Share screen too. So here, so this is, okay, so this is when I open Rhino in the Grasshopper file. You see my screen, right?
Yes.
Okay, and then in the file, special folders, component folder. And this now opens up all the components. And then sometimes, like if you go on one of the components, here there is a lock or unlock. So mine are unlocks. I never had that kind of problem. But sometimes this happens with external plugins.
Yeah, I went in, not within Rhino, but within like the plugin that I downloaded from the drive, I went and made sure that in the same like attribute section, like it wasn't locked or anything. But it's still not letting me download it or install it.
So it is copied in your libraries folder, right?
It is not. It's just in my like computer downloads.
Okay, so what if you just, it's in your computer downloads. What if you just copy them from where you have downloaded it, open Grasshopper,
okay,
go to special folder, component folders, and then paste them here.
Okay, I will try that.
Yeah, okay. Yeah, I mean, this is the way I install these like outside plugins. It doesn't have the automatic installation. You need to copy them and paste them in the libraries.
Excuse me, I have a question.
Yes.
I tried to do the second way, first making the paper wet and then adding the tape, but it didn't really make any wall.
It's really soft now. It should dry, right?
Yeah, but
Is it dry now or no?
I think, yeah, it's almost dry, not fully dry,
But give it a little bit of time.
Mine is still drying, so it's getting there.
Yeah. Yeah. So it's, yeah, it is very slow at the beginning. So it would be good to put it somewhere a little bit warmer in front of your laptop fan, or just set it aside. It should bend.
Okay.
But it should dry and then it will bend.
Yeah, and I would say that usually things work better with a bit thicker paper, because maybe you placed it somewhere where it's too. Well, actually, how can I see it again? Your piece.
I made a L shape. Yeah.
Ah, okay.
To check the different directions.
Yeah. Okay, so I'm not sure, but it could be that it's too long where the self weights becomes an issue. So try it out with a more simpler configuration first, like a shorter strip, just to test that it works, and then or maybe even try it with a thicker paper, because I think it's probably too weak if it's so thin to lift all that.
Okay, and excuse me, when should we add the tape? Because I think maybe it was too wet to take the tape.
So I just spray it, and then I kind of make sure that it's evenly coated, and I also just wipe away the wet water on top so that it's not, because if it's too much moisture, like too much free water, then it's also hard to tape. I kind of just soak it or spray it so that it's saturated, and I wipe off the extra water and I put the tape on.
Okay.
Yeah, so that the tape sticks. Okay, we have 2 or 3 participants one or two participants that didn't talk so much. So be prepared, I'm going to call you out soon. To show you things. Yeah, because it's good if we work together.
Sorry, do we have to download Congru Physics? That's the right plugin? The name is Congru Physics?
Yeah, Kangaroo Physics, I believe. Yeah.
Oh, thank you so much.
Or, yeah, Kangaroo 2. Kangaroo Physics is the general term, and then there are different versions. So you need to download Kangaroo 2 separately. It comes with the Rhino and Grasshopper and Rhino 6 or later. But if it's lower versions, download Kangaroo 2. And the other files are in the folder, the things that you need to download. And the way to put the plugins, again, is to copy them and go into the special folder, libraries folder, and paste them. I will share my screen. So you will open Grasshopper here from the file, go into special folder, component folder, and then here you copy all the files from that resources folder, copy them and paste them here. So if you couldn't make it work at the moment, it is also fine. This file is very simple. So you can also try it later today.
Sorry, I lost my connection. Can you repeat it, this part? You're talking about how we can get the Congru?
Yeah, so I was saying that here is this resources, right? You copy all of these files, like you download them, copy these files, and then open Rhino, open Grasshopper. In Grasshopper in the file, and then special folder, components folder, you open that, and you paste all the files there. So the files that you copied from here, you paste them here, and that should cover all the components you need. Kangaroo 2 is something
Okay, thank you so much.
This is the link that you can find Kangaroo 2. Yes, it's Kangaroo Physics, and then the latest versions. Oh, I need to log in. Okay, I just put Kangaroo 2 also in the same folder in the example files. So with Kangaroo 2, again, it's a zip file. You open it, you copy this Kangaroo 2 and the DLL version, you copy them and you paste them in the special folders.
If we have
Okay.
Rhino 7,
Yeah.
do we have to install Kangaroo 2?
No, it'll be included already.
Okay.
I'm pretty sure. Let me double check, but I'm pretty sure that it comes with.
Okay, so I lost track of time a little bit. So let's let's look at this file quickly, and then if you have any issues with the installing or something, we can go through them later after 5 maybe. So let me share my screen again and show you this file. Okay. So hopefully, if you were able to download everything, you are able to open this file and here the Grasshopper basic bilayer bending. So you see on the top, there are some nodes, and these are the dependencies, the things you needed to install. Then there is this part for meshing, and then this lower part for simulation of bilayer bending. So we will go to that meshing later. Let's look at this part now. You do have, in a Rhino file, you do see that we have a mesh, a very, very simple mesh, and we have a line, and this is, we call it basic bilayer. Here, if you look, we have this area called setup. In this setup, you will need to have a mesh, an actuation, which is a number value, and an orientation. So this mesh is basically the piece of paper that you have, or this mesh, the thing that you want to simulate the bending. This actuation value is the amount of bending. So as you saw, some papers bend more, some of them bend less. With this slider, you can control that. The slider is called value. And then you have a third component, which is the orientation. And this is the fiber orientation. the bending orientation. So these are basically the main things if we want to simulate a simple piece of bilayer that has a basic mesh, a bending value, bending curvature value, and an orientation. If you go a bit down in the setup, we have two more things. I'll get to that in a moment. Whatever setup we have here will go to a solver. And the solver is a kangaroo solver. It's a physics solver. So you define some goals for it, you define some constraints for it, and then the solver solve these like physical constraints and simulates the motion and give you a final mesh. Let's take a look here at what happens if I run this solver now. In the basic setup, you see two things connected. One is a button that goes to the reset. So you always want to reset it before you start the simulation. And then there is a true or false toggle. So by changing this to true, you basically start the simulation. So let's check it now. So here you see that it is taking some time, and in the time iteration, it is visualizing this bending motion in your paper. If I go back, and if I want to change something in the setup, for example, orientation. So the okay, sorry. The orientation, we control it with this line that we define. So when you open these two files together, they are already referenced. If they are not, you should reference them, meaning that on the mesh, you should right-click, should set one mesh, and from Rhino, you click on your mesh. And the orientation, same. You right-click, set one curve, and then you click on the curve in the Rhino. So this was the thing that was already like set up in the file the last time I run it. But now if I want to simulate how this piece bent, if the fiber direction is different, I can go to Rhino and I can rotate this line. So if I rotate this line a little bit, this will now simulate a situation that I have a bilayer like this, and I'm cutting it from a piece of paper that the fiber direction is kind of like 30 degrees, 45 degrees. So I go back to the simulation, to the solver, I reset it, and I run it again. And now here you see that it is bending diagonally. So if this was now a long piece, long, like a mesh like a strip, you could see it start twisting. Okay, so this was the very, very, very basic. You will have a mesh, you will have an actuation value and an orientation. Actually, let's look at what happens if I increase going. And this file it's a little bit heavy, so my computer freezes a lot. You might also experience that, but just give it a bit of time. So if I now increase this actuation value, which was one of these 3 points in the setup, and I go restart again and run it again, you see that our flap is bending more. Okay. And then let's just look at these two other things that we had in the setup. One of them is the anchor point, which is now connected. So the anchor point is if your flap is connected to something, it's like anchored at some point. the reference is 1 point. So here again in the file, I have already referenced it to a point on the corner of the thing. So here, set 1 point, this point on the corner. If you want another point, you can simply draw a point on Rhino and then right click on this, set 1 point and set a different point. You can also, yeah, let's check how this goes now. So now you see that the part is connected to the other point. It's like anchored on the other point. You can also remove this. So as I said, your solver kind of merges different goals that you have. If you don't want to have an anchor point, you can just disconnect these two. And in order to disconnect, you push on on Control, and then you go from this component to this component, and it disconnects it. If you want to connect it back, you push Shift and go from this component to the other component. So I will disconnect it now just to see how, if we don't have any anchor point, well, actually now it is kind of staying because the piece is standing like that. But it gets disconnected. It is not constrained to any point anymore. And the last goal that we have here, which is one of the things that the solver takes into account, is a floor goal. So this basically defines that there is like a floor on the XY and the XY plane on Rhino. If you disconnect this, you just disconnect. You will see that as the thing bends, some of this goes below the XY or the Z or 0 plane, and some of them on top. So it doesn't matter, you can keep it connected, you cannot. I like to have a floor, so I keep it connected. So this is pretty much the basic setup on this like basic mesh that we have. But if you want to simulate it on another piece, like on a long stick or something like that, so what we need is a mesh as an input here. And we want our mesh to be like non-directional, be kind of a random mesh. And this is what you can generate here. So the way this step works is that you can draw the surface that you want in Rhino. So like I'll draw something like this. And the surface that you have in Rhino, you come and you reference them here. So I click on it, come here, set 1 direct. And this component, again, there is a reset button, so you reset it. And then this gives you a mesh. So what we do here is that we bake this mesh to send it to Rhino. And now if you go to Rhino, you have that surface and you have this new mesh. And you take this new mesh wherever you want, and you can come back to this bilayer setup and reference your mesh. So here I set 1 mesh. I need a line for bending direction, for bending orientation. So I draw this line, I set the curve. The actuation value, I keep it the same. And here, I can visualize now this strip. So then you can basically draw any kind of mesh that you want, and you can reference them in Rhino. From Rhino. So do you have any questions?
I have a very stupid question. So at the very beginning, when I load the GH file, actually I only see the stuff in the Grasshopper window, but nothing in the Rhino window. So I'm not seeing the mesh.
Do you open the basic bilayer bending Rhino file as well.
You mean the 3DM file or?
Yeah, the 3DM file.
Okay.
So you should open that and then open the grasshopper.
Okay, I see. Okay, yeah.
Okay.
This should work. Okay. Yeah, I'm not familiar with it.
Yeah, I mean, we can stay. I think we can stay longer after 5, or we can.
Okay.
Something between.
Yeah.
Other questions? So I mean, I think the difficult part is really to like install this and open it. But as soon as we do it, I think the rest should be pretty easy and intuitive.
Did everyone try drawing a shape and then meshing it, perhaps? I think it's pretty clear with the files that are already in the 3DM, but maybe a bit more complicated is the meshing part.
Excuse me.
Yeah.
I have a question about the actuation part. So I have previously worked with Kangoo, but trying to understand how it's making this kind of formed shapes, curved shapes. So how are you making this actuation? So because we are making it like what moisture does.
Yeah, okay, so if you want to know that, so this is, so with the rectangular tool, there is the possibility to define your own goals. Oh, I'm not muted. Okay, so you can create new goals. And basically what we have done is that we have defined a shape matching goal. If you go into these components, it kind of like, let's see if it shows or it doesn't show. But basically what we do in this component is to make a bilayer structure. So we give it some, we first give it some depth, some thickness to this mesh to make it 3D mesh. And on one side of this mesh, we scale the mesh faces. So this kind of scaling is the same thing that happens in the paper, that it is expanding or shrinking, right? So you see here that we say this bottom layer is staying the same, but this top layer, all the faces are shrinking. And then in the shape matching goal that we've defined in the kangaroo is basically saying that try to bring all of these mesh faces together again, like connected the same way it was connected before. So this way we are saying that this upper layer, we are like shrinking it, and this like the solver basically solves how these faces can go back together, and to do that, the overall structure needs to bend. So it is not really like a very precise simulation. Actually, it's not at all. It is for visualization and as a tool to design. So you can't say that, for example, we have wood with this property or 3D print with this thickness and how much bending it has. This tool cannot do that, but it can solve this question, solve this like problem with pure computer graphics, so that you can visualize what will happen and what happens if you change the bending direction. Yeah.
Is there a specific reason that you divided the plane into kite shapes?
To
and
the
not
kite
like
shapes here.
Or not like mesh into the triangular?
Okay, so the thing is that when you saw here in this, so here what we do is that we are like shrinking each of these mesh faces. The thing we want is for these guys to be absolutely random, don't have any special directionality or any special form or something. So that overall they work together as this like bilayer structure. If your meshes are all like aligned and then they scale in one direction more than the other, it messes up things. So we use this like this meshing things on top so that we can have like a nicely divided mesh overall, and also not directional.
Right, thank you.
But actually what we will show you tomorrow for the origami, there you see that it's really important if the mesh faces are like aligned as rectangular meshes, because we want to fold them on the lines and define hinges. But for this basic bilayer, we just go with a random mesh.
And in this definition, the thickness matters of the material?
We can't really define it, no.
Oh.
There is no way that we can define the thickness.
Excuse me, I have problem with some of the components. There are just white and I can't see what is that. I think the problem is about the installing. I don't know. The component that is above the part of the solver. Yeah. I can't see this one. This is
when
just
you open
white.
the file, did a message appear saying which?
Yes,
which
but it couldn't download the files, and I think this is the problem.
Do you remember which plugin was it?
I think the Congru Junior. It was something like this. I have a Rhino 7, and I think there is a Congru 2 file.
The Junior is, or sorry, is in the resources file. So did you?
Yeah, I copied that file to the folder.
Oh, by the way, for the zombie thing that you see above, I don't believe we need that, right? Yessie, we're not using that.
No, the zombie, we don't really need that. You can just delete it.
That's not just this component.
Yeah.
Something else.
So if you maybe close the files and open them again.
Okay.
And then tell us which component is missing. So the way to go is that if it's Congru Junior, just Google it. I don't even know what Congru Junior is, but whatever is missing, you should Google it. And
I think Kangaroo Junior is actually related to the zombie solver. So so if it's asking for that, don't worry. Everything else should work.
Okay, I will check it. Thank you.
Hi, would you mind running over how you got the pattern on the plane surface? The step when you drew the plane and then...
Oh, yeah. Yes. That was here. So you have the plane. This is what we have here on top, on meshing. So you go here, you need to reference an input brep, and at the end you get a mesh. So you draw the brep in Rhino. Here you right click, set one brep, reference it, and here at the end comes the mesh. But before that, you should hit this reset button. So when you reset it, it generates the mesh. And then you come here. So this is the mesh with the pattern. You right click on it and you bake it. And when you bake it, it now brings it to the Rhino. So now in Rhino, I have surface and I have a mesh.
So I think I have the component between the two meshes missing. So I did the initial step, but I wasn't able to see the pattern.
Oh, this is Weaverbird.
I don't think I have it installed. I think that's the problem.
Oh, no.
I'm just going to do that one.
No, this is our fault. Oh, shit. I should have put it in this resources. Okay. So, guys, you either need to look for Weaverbird, Grasshopper, and find it on Grasshopper 3D and download it, or I will download it and put it in this folder right now.
So that's the component for making these kite patterns that someone asked, which I think is relevant for this example, the simple example, but tomorrow we will actually make our own mesh patterns with the rulings.
Yeah, to be honest, for the origami, you don't need these. This is for this like basic exploration of bilayers. For tomorrow's tutorial, we don't even need these. Okay, I sent a link here and you can download the piece. I mean, it's a cool tool to have, so I suggest that you make it work on your computers because it can also help you design it. You can help with that too. Okay, so we're a bit short in time, so maybe I should go ahead to the Kirigami lecture so that we can finish that part by 5. But then if you want to stay longer, we can stay longer to do some troubleshooting. Okay. So is everybody here? If you're here, raise your hand. Awesome, yay. Oh, it's great to see your faces. Okay, so let me close this and go to the Kirigami lecture. All right. Okay, guys, if you have any points to say, if you have any questions, please unmute yourself and go ahead now. If not, I will start. Okay, then I will start. All right, so let me talk to you a little bit about Kirigami and how we can make self-shaping Kirigami. Okay, so what is Kirigami? Well, Kirigami is a variation of origami, the ancient Japanese craft method that allows cutting the paper. So origami, if traditional origami only includes folding a single sheet of paper, Kirigami is a variation of that allows cuts in the paper. And basically this cutting is the primary method for creating designs. It can include folding. It can include folding in the final piece, as you see in the left-hand side, or it can use folding in the process of creating a piece. For example, as you see in the right-hand side, where you cut a piece of paper so that you can create cuts more easily throughout the whole piece, or it can just not include any fold at all and can just be a nice 2D piece of nicely cutted paper. So let's just take a look at some examples of Kirigami, just some nice photos to look at. I have put the credits on all the slides, as you can see, and if you are interested to look more at these examples, please feel free to visit these references. But as you can see, it can be some cuts combined with some fold or bending on a piece of paper, or it can become more complex formations that turn paper into 3D structure. Here, for example, you see a famous type of kirigami, which is the pop-up kirigami. Maybe you remember it from some like postal cards, or even some books that we had when we were kids. So this is kirigami when it's with the paper and as its original craft. But what I wanted to show you here is the fact that kirigami is today inspiring engineering and science and technology, and it's going way beyond a form of art and craftsmanship. For example, here you see a project and paper from Harvard University that uses Kirigami pattern to create structures on the surface, similar to the structure on the skin of a snake. And then through this specific patterning, it creates locomotion for a robot. So the red examples are these soft robots that they have developed based on this Kirigami pattern. Here you can see a similar pattern. This is again from the same group at the Wyss Institute at Harvard that now apply this pattern on a shoe sole, and this changes the grip and the friction of the midsole to the ground. Here you can see some nice patterns of Kirigami that are produced in the nanoscale. So they have used some laser and cutting and fabrication technology in nanoscale and create the super intricate patterns based on cutting a sheet of material. And these patterns create crazy optical characteristics. So this whole paper is about creating this nanoscale Kirigami structures and what properties they bring, what optical properties they bring to in the macro scale in the material. And lastly, some other work from this one, and also from Harvard University, that they looked more on the mathematics and the modeling of this Kirigami. And really, the idea here is that a piece of paper can be shaped into any shape by creating strategic cuts to it. For example, here, going from a square into a circle. And they were mostly focused on this kind of mathematics and modeling of how to transition from one to the other. But the very interesting thing about Kirigami, which makes it different from origami, is that in origami, you fold a piece of paper and usually go lower in terms of volume. So that you start with a big piece and make it smaller and smaller. But with the Kirigami, you can create cuts, and this cuts allows you to expand a sheet of paper. And then by how these cuts are oriented, you can create different expansions. So these were some inspirations and quick looks at the Kirigami, but what we are interested in is self-shaping Kirigami. So so by now you know our method for shaping, which is based on bilayer bending, and this bilayer that is like the piece of bilayer that goes from flat to bent upon moisture or other kind of stimuli. So basically what we're looking here is how we can combine this form of actuation, this form of shaping, with Kirigami inspired patterns and mechanisms. So first I'm going to show you a video of some of our work at the ICD. These are the 3D printed structures. They contain cellulose, so they are moisture activated. And here you see. Do you hear the music? Oh, no. Okay, then maybe I should talk. So here you see the strip, similar to what Tiffany showed you with the paper, with the S shape, and then a combination of those strips, which make this kind of like expanding patterns, and these patterns are all inspired by Kirigami. Here, a single ring, and then these rings that are aggregated on top of each other and create this self-shaping spatial structures. Next, this one is a simpler version, but this is not a structure that expands and shrinks, but instead it's composed of a bunch of flaps. And these flaps open as they get wet. Actually, here they are with the material that are temperature sensitive, but it doesn't really matter. So here you can, for example, think that these can be on a wearable on the body that respond to body moisture, or in architecture, they can be on a building facade that they can open up. And there are even some works that use this self-shaping Kirigami techniques to create locomotive robotics, soft robotics. Here's a work from the Morphing Matters lab at Carnegie Mellon. And here, which is like most relevant to us right now, is self-shaping Kirigami with paper. And I'm going to show you two examples here. So the two examples I will show, they are included in that patterns, Kirigami patterns Rhino file. So if you want to get the pattern and if you want to try it yourself, you can do that. So what I'm going to show you here in this slide is this, this prototype and how I made it and how it's working. So let's first take a look at the video. Yeah, okay, so I'm spraying water. I sprayed water from behind because that was the side that paper is exposed. And you see all of these flaps that they open all at the same time because I'm trying to put the water kind of evenly everywhere. And as I spray more water, they open a bit more. So this was a simple example that I just made to show for this workshop. I think I made the whole thing in half an hour. So in the Rhino file, you can see the pattern. Okay, so how we can make this, how we can make these kind of structures, we start with a design. You can either just sketch it by hand, or you can draw them in Rhino. I drew them in Rhino. The thing you need to keep in mind is the fiber directionality. So if you want to make this piece, if you want to make a design out of one sheet of paper, you know, in one sheet of paper, you have a single directionality. So this is why I oriented all of my flaps in one direction, knowing that I will orient them in a piece of paper with this kind of direction so that the flaps will open upwards. After I made the design, I need to transfer this design onto a paper. So the good way to do it is if you have a printer, you can just print it on the paper you have. If you don't have a printer, this is what I did. So I just take a piece of paper. I have already marked the fiber direction with my paper, and I just put this paper on top of my monitor. So I zoom in and zoom out in Rhino to have the size I want, and I put the paper. And since there's light coming from your monitor, you can kind of see through and then draw it by hand on the traces. And this is exactly what I did. So here you basically transfer your design from Rhino to the paper with a pencil, something. And then the next step is to apply the tape. So you want the tape to be applied everywhere that the flaps are, and not the rest of the paper, but tape. So here what you see is just me putting tape all over everything. And in the next step, I cut the outlines, and I also cut like here around the tape, and I remove the tape from everywhere other than the flaps. So at the end, your paper is staying flat, and the only parts that bend are these flaps. And you can see that these parts are shiny. These are the parts that have the tape, and the rest of it is just not shiny. And yeah, that's it. That's basically it. And then I put it, oh, sorry, I can't play the video now. Well, this was the same video. So I just put it in a frame to, to kind of constrain the rest of the paper, because when you splash water, the rest of the paper might also bark. It's a normal paper, so it's good to put it in some sort of frame or somehow constrain it so that only the flat parts move nicely and the rest of the paper stays. And that's it. So that was the main thing I wanted to show here. And what I'm going to show you live is the other pattern of Kirigami that you can find the pattern in the file. And I also made it here, so I can just give you a live demo of that. So this is a simple pattern of this kind of expanding Kirigami. And you can see like the cut file here in this image and how it looks when it's opening, and you can also see the pattern from the folder. So let me stop share now, and I will switch my camera and show you the piece here. All right. So here was my Kirigami. So actually I made this right before our workshop and I sprayed water in it, and I think this is still not super dry. But what I'm going to show you now is that if I put more water on it, if I spray more water on it, you can see that it's, oh no, this is not showing so well. Let me switch my camera again. Okay, so the good news is I have another one. So I have another pattern that I'm going to actuate it right in front of you right now. But before doing that, I wanted to talk about a few points. So the first thing I did was that I transferred this from Rhino onto a paper. The thing you see here is that these parts, some of them are bending upwards, some of them downwards. So this is what we just experienced, that in the strips, you need to put tape on this side, the other side, this side, the other side. So what you actually need to do is that you need to put tape on some of these faces on this side of the paper, and then on the other faces on the other part. So the first thing is that you need to trace your lines on both sides of your paper, as I have it here. So what I do is just I put it on the monitor, draw the lines, or draw just the point lines later, and then flip it and draw the lines on the other side. Then the next thing is that in the pattern, if you look at the original pattern, or if you look at this like bent file, you see that the parts are connected to each other, every other one. And the ones that are connected to each other, they are bending in the opposite direction. The way this translates into self-shaping is that in this strip, I have convex, concave, convex, concave, meaning that here, no tape, tape, no tape, tape. And if I now reverse it, you see now this first one doesn't have tape here. And you flip it, you see that it has a tape on the other side. So this means that this first row, this is now going convex, concave, convex, concave. And then in the other row, you kind of go, you shift this list. So the two faces that are near each other, this one has, this one doesn't have tape, this one has tape, this one doesn't, this one has. So at the end, this looks exactly like a chessboard, right? It's like black and white, so it's not really black and white, but tape, no tape, tape, no tape. And this is how it looks when it's flat. So now let me actuate it live. So what I'm going to do to kind of be able to hold it nicely is that I have some stakes and I'm going to clip them. Yeah. Just somewhere so that I can hold it nicely and that I can also show you well. Okay. So yeah, with this shiny thing, you can easily see which parts are filled with and which parts are not. And here we go, the moment of truth. So I splashed it from both sides because some sides have tape on this side, some tape on the other side. Yeah, here we go. I use like a little bit thick paper, so it's taking a bit of time. With the thin paper, this would be faster. Yeah, and unfortunately, these guys that are constrained on top, we don't really allow them to bend, so this is why you don't see those guys bend. But on the bottom, I think they look better. Okay. So again, you can think of different scenarios of why you would want a surface to be like this, to like increase its porosity, expand, shrink as it's getting exposed to stimuli. And these are actually the topics that we're going to talk more when you go with your project idea. But yeah, this was then our live demonstration of this Kirigami. I also have the flaps here that I can show you one more time. So yeah, I have this kind of frame. Otherwise, the whole thing will get really fluffy. So you can see them slowly opening. All right.
They're really interesting, these models that you are showing. I have just one question.
Yeah.
Now?
Yes, of course.
Yeah, because we are using tape to make bilayer for paper. I want to know for, maybe you told it, I don't remember. For wood, I want to, for example, using plywood, do we need to add another layer? I think you told something like plastic. And how are we doing this? Can you explain about this part?
Yeah, so I think actually Dylan will talk more about this in his lecture in 2 days. But with the wood, we also need to have a passive layer and active layer. So you can have both of them with wood, but with wood in different directions. So wood expands in one direction. So that would be like your active layer in this direction. You put a piece of wood in the opposite direction that doesn't expand in that. So we can have wood bilayer. You can also have wood metal bilayer. You can have wood glass fiber bilayer. This is also one of the very, I think this is how some of the smaller scale ICD prototypes were made. That yeah, we have glass fiber and resin, and we put it on a piece of wood. Glass fiber resin is restricted, and the wood is expanding and shrinking, and that makes the bilayer structure.
Yeah, okay, thank you.
Hi, I have a question regarding wood again. I think I've seen a couple of my friends trying prototypes with paper-backed veneer. So it's basically veneer and paper. How do you have you guys tried something with veneer and paper, and how does it work?
Are you talking about wood veneer?
Yes.
Yeah, wood and paper bilayer.
Yeah, so actually we haven't really done that because both materials are hygroscopic, and usually, for example, with the paper and plastic, it's because one material is very different from the other material, so that the motion is most amplified. So I think, I mean, I personally don't think that it makes so much sense with the paper and the wood. But if you're interested in, well, the reason why we also are using paper a lot is because it's so easy to cut and work with. So if you're also interested in using wood, it is possible, but you kind of need access to like some wood shop or something like that. Yeah, then you can use wood glue to glue wood to either other pieces of wood, like Yasi said, in opposite orientations, or metal, or the resin, which is kind of not so nice to work with, to be honest. Or, I mean, you can try, if you have a piece of wood and paper, then go ahead and try it. The only issue is that there's a mismatch between the properties of wood and paper. Paper is just so much weaker. It's also hygroscopic, but it doesn't have swelling force as wood. So to our mind, it doesn't make so much sense. But I mean, feel free to try it out. That's how
I just seen someone trying it at like the workshop at my university. So I never paid attention, but now that I'm attending the workshop and I saw wood and paper and you speaking about it, so I didn't know if there was something specific in the properties. Like that's exactly what I thought, that both are hygroscopic. So how would it work?
Mm-hmm.
So I was just curious.
But feel free to try. I mean, not to discourage you.
And of course.
Any other questions?
So can I ask a question?
Yes.
Yeah. So is there any material which is not like wood? I don't know what it is called, like naturally made or organic made, some kind of a polymer or chemically made material that also has the same properties in terms of bending.
Yes, there are many. So one like the first question would be about stimuli. There are some materials that respond to heat. There are some materials that respond to humidity. So on the top of my head, I can say the whole family of shape memory polymers can have this kind of shape-changing properties. They respond to heat, but they expand and shrink with the heat, and the same method that we showed with the bilayers. We can turn them into bilayers, one with shape memory polymers, one with normal polymer, and they bend with heating. With the hygroscopic stuff, well, wood is natural material. The 3D printing things we showed you are like semi-natural. They're a mix of polymers plus wood powder. The better versions are polymer plus cellulose, which is cellulose powder gotten from natural sources, and there are also hydrogels. So hydrogels are also based on cellulose, but they're like heavily chemically worked on, and hydrogels expand a lot with the moisture, so they are a good material for this kind of shape-changing things. But the problem with hydrogels are that they get really soft when they're wet, really soft. And there are also other materials. Yeah, but these were at least the main ones.
Thank you.
In my head. Okay, so let me say some stuff before it's 5. First, we want to give you a small homework, and we want to ask you that by tomorrow, try a self-shaping kirigami in your own. You are constrained to one piece of A4 paper, so you can't go bigger than that, but you can also cut it in half. So A4 or A5 is what you have to work with, and make something, make a self-shaping kirigami. You have the 2 example files, and you can also go with whatever you want. the idea here is to combine bending and Kirigami patterns. So some Kirigami patterns don't work because when you like stretch them or when you fold them, they don't have any bending in any parts of them. But some Kirigami patterns work like magic. So this would kind of be your task. So A4 or an A5 by tomorrow.
Do we have to recreate this pattern or make up a new one?
No, you can make up a new one.
Okay.
You're completely free in that. So that is the first thing. The second thing is that for the digital part of tomorrow, we're going to have a grasshopper file. And this grasshopper file, actually the base of it, I learned it from an amazing YouTube video tutorial, which is around like 40-45 minutes. So I will also share that file with you. I will email it to you right after this workshop. And if you manage to watch that before tomorrow, that would be very helpful because this guy walks you through like why all the components are there. And then tomorrow we can save some time. But that's up to you if you don't want to do it. So these are the two things that we want to prepare for tomorrow. And yeah, now you can go ahead with any questions that you have. If you're behind some parts, I can stay as long as you guys want to stay and we can work them out. If not, we can just leave. Okay.
I just wanted to thank you both. It was a very interesting session, and I hope the next days will also be very interesting, and I learned a lot.
You're very welcome.
Thank you so much, both of you. This was extremely interesting. I mean, the things we could do with paper is just unimaginable. So this, I didn't think this would work, but it did. So I'm really excited.
Oh, nice. How is the L shape of somebody working? One person made an L, did it? Oh, yeah, nice.
Yeah, also I wanted to say that, I told it didn't form, but it really did.
Oh, yeah, okay, great. See, it was not dry enough, yeah.
Yeah, thank you, Yassi. Thank you, Tiffany. This was very amazing.
Thank you, guys. Thanks for joining.
Thank you so much. I learned a lot. Thank you so much.
You're welcome.
See you tomorrow.
See you
Thank you,
tomorrow.
guys. See you tomorrow.
See you tomorrow.
Bye.
Bye.
Once people log off, because this is more of like a question pertaining to me and I guess troubleshooting, I'm still having some issues.